Hi guys, and welcome to today's video. Within this video, we'll see the different internal exceptions supported by the Cortex-M microprocessor, as well as the different root causes behind those exceptions and how to cut them. And we'll finalize this video by a demo running on STM32 microcontroller. As you can see here, this is the Cortex-M vector table structure. Now the first 16 entries from initial stack pointer entry to SysTick timer entry, those are what is called internal exceptions. Initial stack pointer is not part of those internal exceptions, of course. Reset, yes. NMI, HardFault, memory manage fault, BusFault, user fault. Then we'll have the supervisor call. This is reserved for debug, to be more precise, debug monitor if it is supported. Then we have the pend SV and SysTick timer. All of those, from reset to SysTicks, are considered internal exception to the Cortex-M. Open the execution on one of those exceptions, the CPU will switch from the application code to the exception handler code. Or the exception handler will be running on handler mode, as we can see here. And for the typical use case, the application will be running on thread mode. Hence, whenever the CPU receives one of those exceptions signals, then it will trigger a switch from the thread mode to the handler mode to serve those exception service routines. In terms of fault exceptions, we have four types of faults. We have first of all the hard fault, then user fault, then memory manage fault, and finally we have BusFault. BusFault in general is generated whenever we try to access some forbidden or not mapped address. Memory manage fault in general is generated whenever the CPU tries to access some MPU protected memory region. User fault, on the other hand, may get generated if we try to execute unsupported instructions, for instance. Finally, the hard fault is kind of fallback for all those kind of faults. Means if there are kind of events that are not covered by those faults, then this will trigger a hard fault. Also, by default, all those internal exceptions will be escalated to hard fault unless we explicitly enable the catching of those exceptions via those SCP registers. NMI, or Non-Maskable Interrupt, is the second higher exception after reset. If you remember, within our vector table we had the first entry mapped to the initial stack pointer, then we had reset, and then we have NMI. This means that reset will have always the highest priority, and it will be able to preempt any running code, whether it is running on hard fault handler, BusFault handler, or even a main application program. The reset will be able to preempt any of those programs. Then we'll have the NMI. So even if we are running basically on hard fault handler or BusFault handler, then we get an NMI exception. The NMI will be able to preempt those ones. The NMI is asynchronous in respect to the execution flow of our program. And in most of the cases, the NMI will be connected internally to some signals coming from the system on chip product, and to be more precise, to some failure-based events. SVC, or Supervisor Call exception, is another type of internal exceptions supported by the Cortex-M microprocessor, and mainly used by the user-based application to request certain services from the operating system. Hence, the body of the supervisor exception is in general part of the operating system. To request those services from the operating system, the user-based application will need to invoke this SVC exception with certain number, and this number will represent basically the service number that we want to request, and it will be embedded as part of the instruction encoding itself. Then the operating system will be able to catch this supervisor exception call and serve basically this user-based request. So guys, this is our Keil-mdk project, which is C-based one and compiled for our Cortex-M based platform. The hardware is an STM32 microcontroller. The program has been compiled and loaded and ready to the STM32 flash memory, and this is our debug session. Right now we are in the reset ISR, and we're gonna jump to our main function, and here actually we are triggering a fault. We trigger this fault by accessing some forbidden basically address or not mapped address. So this FFFF is not a valid address within our platform, hence trying to access this one will lead to BusFault. that will be escalated, of course, to HardFault because we didn't enable explicitly the trapping of the BusFault exception handler. Now let's set breakpoint here. Let's run. Now so far so good. Let's keep an eye on this field, ISR. This field is part of the XPSR releaser, and it does indicate basically the exception number that has been triggered. Now let's run, and here we go. As we can see, we are here trapped within this HardFault handler. This is an internal exception within the ARM Cortex-M microprocessor, and the ISR field has been updated with this value 3. If we try to match this to the structure of our vector table, you can see easily here that the HardFault handler is occupying basically the third entry. Of course, if we exclude the stack pointer part, which is not part of, let's say, of the internal exception handler of the Cortex-M. So this is the first entry, this is the second, and this is the third entry. And 3 is matching exactly the number that has been reported within this ISR field.